So, hello guys. Today we shall be doing this video on the complex plane and complex numbers. And firstly, to understand and know what complex numbers and the complex plane is, we firstly have to understand these three essential, major categories of, types of numbers. There are, of course, natural numbers, where in this case of the real plane, where we have natural numbers being like from up to like 1 all the way to positive infinity, 1, 2, 3, 4, etc., etc. And then this consists of four, like all natural numbers. Okay, let's just say for all natural numbers, for all n. Let's do that. Just gonna highlight it like that, just for like the real analysis of it all. For all natural numbers, where n is denoted as the natural numbers, and this also consists of decimals. For all decimals, I shall denote d. For all real decimals, like 4.68, or even pi as a irrational number. For all irrational, I'm not gonna do it. I'm just gonna do it as lowercase, so that implies pi, the square root of 2, and other numbers that are irrational, and so on and so forth. So decimals, including 1, 2, 3, 4, so on and so forth. That is for all natural numbers, and all sorts of numbers that we're very familiar with as real numbers. Even fractions. For all fractions, I shall denote f, which goes to like 4/5 or 1/2. So note that this sign that I shall be using throughout the video means for all. So I'll just keep that there. So imaginary numbers, in this case, are actually different. I mean, you could be familiar with this, but we'll just have a brief introduction. We all know that, for example, squares, for example, 4 squared is equal to 16, and to take the square roots of both sides of these, we know that 4 would be equal to the square root of 16. Yes? So whatever number, regardless of it being positive, some number, negative nth, and we square that, that will always get us to like some n squared. And let's just denote that n squared as being some square number that is either has a root of negative n or positive n. For positive n, squaring that will also get us to n squared, regardless. So for us to actually have the square root of -1, in other words, we need some root that gets us multiplied by another thing to get us the -1. That doesn't necessarily exist in our real plane. And instead, mathematicians, upon discovering this, have denoted this as I, standing for imaginary number. So this, is technically actually a real number. It's just an extension of the conceptualizations that we identify by the means of numbers in general. And this is just a single category. And imaginary numbers combined with real numbers get us to complex. But just for example, we have I. So we have 2i. I'll just put in, like, for example, 2i. Or I can do 68i. It goes on for, we can do as many numbers for it, as many numbers that are actually kind of like coefficients to this I. And remember that this is the same thing as 2 times the square root of -1. This is the same thing as 68. Sorry. This is the same thing as 68 times the square root of -1. And it goes on forever, all the way up to some n, like plus or minus n, to plus or minus n, that being I, times I. So it can just be anything. And that's the same thing as saying plus or minus n times the square root of -1. Because the square root of -1 does not exactly, we could say, defined in the real plane, so we cannot identify this in the real plane. And instead, we have made our own category of numbers, which are known as imaginary numbers. So I'm just going to erase this. This is not needed. Just going to put that identity as well. And finally, we have complex numbers, which are essentially a combination, here's my favorite part, of real numbers and imaginary numbers. And that's where the complex plane gets into. So real numbers plus these, plus or minus these, well, any complex number can be of the form z is equal to a, where a is some actual real number that we've defined by, plus or minus bi. And remember that this is the same thing as saying a plus or minus b times the square root of -1. So this always holds. So we can actually have z, for example, where z is denoted as the complex, some complex number, and this can be like 2 minus 4i, and or maybe even 68 plus 72i, and it goes on and on and on. And the way we actually graph these points through the complex plane is somewhat counterintuitive to how we usually put coordinates for the case of real numbers, which is usually, for example, if we're to have some small axes, so x or y axes, we usually just denote these points. For example, let's just say that point would be 1, 1. So that's how we usually denote like certain coordinates, where we have certain points like here for 1 and the y coordinate being 1. Fun fact, this any x coordinate is known as an abscissa, and any y coordinate is known as a ordinate. So I just wanted to give you guys that fact. So this can be expressed as, well, any complex number can be expressed as this. But did you also know, I'll just put it in, that actually real numbers technically are complex numbers, and imaginary numbers by themselves, even though it seems like it, are actually complex numbers. They both fit into this category because we can consider, for example, 4 as having plus or minus 0i, because that's the same thing. It's essentially the same thing. We can just hypothetically put that there. So technically that would make for any, even imaginary numbers, for example 2i, to have some plus 0, because that is the same thing. If it can be expressed of this form, regardless of whether the real part of the complex number or the imaginary part of the complex number is 0, we can still identify these numbers, real or imaginary, as being complex. Okay, so for any z, we can also have z is technically complex if we have a plus some 0i of that form, or some bi plus 0. So in this case, 0 is the coefficient of I, or the constant coefficient of I, where it can be some number, real number, and that it's multiplied, and so on and so forth. So we'll use our complex plane, and I think I should do another video for this, because maybe we won't have time to get into what exactly complex conjugates are, but we could maybe, yeah, we could try. Sorry. So it can be of this form if we were to put some points here. this upward. So, here we shall denote this as RE. Sorry if I just wrote a epsilon, and this will be, I'll just denote that as IM. And that IM stands for what? What, kids? Imaginary! You guys did it! And re stands for what? Real! AL. Okay, so I was just joking there. So, we have certain points here, as we know, and this actually is what the complex plane looks like. So we're essentially taking that entire axes of the real plane and literally flipping them together and placing them on one axis to make just this entire thing so it won't get complicated, and having the imaginary axis as our y coordinate essentially. So this would, if this was just the x and y coordinates, then this would all be real numbers, but on different coordinates on different axes. So this would be I, 2i, 3i, 4i, and 5i, and so on and so forth. And this is negative I, negative 2i, and negative 3i, and negative 4i, and negative 5i. And then we could also denote that, but just, these are the negative numbers, just notice that. So, it will be on this form, but if we wanted to plot a point, a coordinate here, how could we express that? Well, let's just say we wanted to go from the real plane, from the real axis, and let's just say we wanted 3 for this, for our horizontal or real part, and then we wanted, let's just say 5. So let's plot it right there. This would be expressed as saying 3 plus 5i. Now I know we're not necessarily, it looks counterintuitive because it doesn't seem as though how we usually express it as a coordinate. It's not necessarily, we can't necessarily add this imaginary part to the real part because it's the square root of a negative number. That wouldn't work. Square root of -1, as we've seen here, doesn't necessarily exist for the real parts of the real plane. For natural numbers, for decimals, for irrational, sorry, I don't know why I did that, for irrational, and for fractional values. So it just really isn't defined in the real plane. But in this case, we can think of it as being added to this 3, even though we can't necessarily add it to it to get an exact numerical value. So we'll just express it as this, depending on what the sign of this imaginary number is. And it's always expressed in this form. So some complex number is expressed, where z denotes the complex number, is equal to a plus or minus bi, as I've denoted. So, finally, that is all really. And we could just plot another point. Let's just say that would be 3 minus 2i. And we could try and find the midline, midpoint between these two by having the averages between the, horizontal components, which are the real numbers, and the vertical components, which are imaginary numbers, just for fun, just to get in our heads. So let's put this in. So we first have to add these to each other. So that is 3 plus 3, and we know the form of the midline segment, which I'll denote as m. I know you guys usually see this as slope, but it will just be a plus b, actually, sorry, x1 plus x2 over 2, and for the y, for mx, that's the midpoint component of x, midpoint component of y, plus y2 over 2. So using this formula, we know that 3 plus 3 is equal to 6. So that's the real version, that's the real component. And that divided by 2 is equal to 3. And we know that m in imaginary terms I'll just denote as I, is equal to, that would be 5i and then minus 2i, or in other words 5i plus negative 2i. So that's 5 minus 2, that's 3. And we'll just neglect that I so we can actually have our calculations through the means of the real numbers, because it can't really process imaginary since it doesn't really it's not really defined for this arithmetic arithmetic means. So we just do that, and that is 1.5. So that is essentially 3 plus 1.5 I. Can't see it, I'll box it in. 3 plus 1.5 I. And now we just include that imaginary I into the following complex number to get 3 plus 1.5 I. And that is our midpoint between these two. And, okay, sorry, I don't know why I did that. Somewhere of this, like between there. So that is it, really. That's all I wanted to explain to you guys about the complex plane and complex numbers, and we'll see you guys in the next